Okay, we move to the second part.
왜들 좀 눈치치 그건 안 했잖아 그죠?
그래서?
왜들
How about this red yield cell?
지도 모르면서 의미가
This is what I'm going to explain now. We are departing from the analysis here. You see all elements and the oxygen associated with each. And what we want to calculate is the mass balance of melting 100 kilo ore. That is, we want to know, when starting with 100 kilo ore, how much metal we are going to obtain and how much slag we obtain. And to do that, there is one essential assumption to be made. It is for each element, is it reduced or not? And this is the red column. And here we are going to explain a little bit. Of course, here we are, take it from here. The first reduction yields are close to zero because we are speaking of, you remember, Na2O, MgO, Al2O3, which are not reduced at all. Then
red yield means reduction yield.
Reduction yield, yes, yes, exactly.
I'm confused.
Excuse me. And the first one, the only element of this upper series that can be reduced a little bit is silicium. So SiO2, if we add enough carbon, there will be a little SiO2 reduced. And here you see experience says about 2%, can be 3%, but it's not 10%. 2, 3, 4%. And after SiO2 we have V2O5, K2O, of course CaO. CaO is here, is not reduced at all, and TiO2 is not reduced, but you know, here when we have zero, that's our responsibility when we calculate, because each figure must be corrected each time. Huh? I mean, this I did not touch because these values were included in the previous calculation, maybe for another ore. So the red figures here, the red cells, have to be checked each time, each of them. It's not the same when you change the conditions. Huh? And we will see this afternoon when we work on ferronickel, these figures will be different. Now, let's move. These are the, let's say, non-reducible or very few reducible. And here we go to the chromium, and okay, we have no chromium included in that ore, but just to make the remark, chromium and manganese behave similarly if you have both. They behave similarly. In that case, we don't need to consider, because chromium we have zero. So, as to manganese, as I told you, there is the specificity that manganese may be present by two MnO2 and MnO, by two oxides. So I have put two lines, and what you see, it's a bit confusing, but you will understand. The first line, if you go back here, the first line is MnO2, and of course, MnO2 is fully reduced to MnO. MnO2 doesn't exist at all afterwards. And then MnO, this is the reduction yield for MnO. And now we will see how it is considered. But let's see how it is taken into account for the case of SiO2 as well. And you see afterwards in the Fe, in the other ones, in case of Fe, it's a bit similar to manganese because you have Fe2O3, which is of course fully reduced, and this is FeO, which is nearly fully reduced but not fully. But as for MnO2, the higher oxide disappears completely. I say it again to be sure. When you have MnO2, maybe you have no MnO in the ore, but you may have, I don't know, probably not. But I mean, for sure, MnO2 will be reduced fully in MnO at least. What I am just saying, then if you then reduce MnO, which is the objective here, and once you have Mn, metallic, and you have MnO left in the slag, because you don't reduce it completely. You cannot have this, you have zero. You understand? You cannot have three of them. Once you have Mn, this will be fully disappeared. And for the iron, it's the same. In the ore, you have Fe2O3. In the slag, you have some FeO, but most of it will be reduced. And this will be out. You will have only these two.
왜 저리 써야지? 왜? 정확하게 의미를 못 알아듣겠다. 무슨 왜 저리지?
MnO2에서 MnO로 가는 거는 100%가 환원이 된다는 거죠.
되는 건 또 이해했어. 근데 왜 앞에 지금 얘기하는
그러니까.
주제가 의미가 뭐지?
아, 저기 1도가 지금 저 백스라는 데는 저기는 MnO2에서 MnO로 100% 됐다는 얘기예요.
그렇죠.
그거는 무조건
MnO2,
그다음 71% 돼 있는 거는
sorry,
네.
MnO2 is here.
Yeah.
It's fully reduced.
71% 돼 있는 거는 MnO에서 MnO로 되는 게 71% 되는데 그 중에 슬래그에서 MnO로 존재하는 게 일부 있으니까 누가 생각 고려하면 71% 정도 된다라고 얘기를 하는데 그건 나중에 이제 슬래그에서 양을 어떻게 결정하는지 따로 한번 물어봐야 그때 전화할
아니 그것까지 이해해서
네.
앞에 저 코평 그거는 뭐야?
아, 그 MnO가 MnO2가 더 이상 존재하지 않는다는 거지.
그런 얘기했어?
예.
아, 내가 앞에 주인데 갑자기 MnO2는 맞제로 그 얘기했잖아. 그래서
오케이, 프레이지코.
I have a question. Yes, last day you said you just gas is 40 cubic meter per hour per ton. Yeah, the exhaust gas volume.
Per square meter.
Mhm. But if we give some pressure inside of the SAF, is it possible to operate?
Uh,
Give more pressure, so 1 bar and 2 bar.
it's possible, but it's not easy, and it may be, you know, when you have a furnace producing much CO gas, it may be dangerous to
Mm.
put pressure.
When we give the pressure, we can generate more the CO gas.
Exactly, you're right.
And
That's true, but it's difficult and maybe dangerous.
and
Because once you have pressure, any leakage is a big leakage.
Yeah, dangerous.
Because the good way to operate the furnace is to have a slide under pressure, you know, a very slight 5 Pascal or 10 Pascal under pressure, and to suck off the off gas. So you cannot have leakage in the hole, in the operation hole.
And you said when remaining some gases inside of SAF, and it is one of the burden when we operate it. Yeah. So we give the pressure inside of SAF. It is also the burden, or it helps the CO generation. Burden or power to generate the CO gas.
I don't understand it, because if you don't want to put pressure, the CO gas is the result of the reactions. I don't understand your question.
This is SAF.
Yeah.
We give it some pressure, for example, 2 bars.
Yeah.
And
Yeah.
and you said here is that there is some much gases.
Yeah.
It is one of burden, yeah?
Yeah.
And when you give the pressure, we close the all things. And
Yes.
just gas. It is also, I would like to know, that it is also burden,
Yes, you're right.
or the power to generate CO gases.
Yeah.
This is.
Yes, you're right. If you put really pressure in the furnace, you will be able to pass more gas because it is under pressure. Like the blast furnace. The blast furnace, you put blast furnace at a high pressure, have more productivity. But having this pressure under safe conditions is not easy.
Not easy.
It's not easy.
And if we do not, if we charge the MNO, not MNO2.
This is. But okay, we can check. You will need a bit less carbon, but as I explained to you, the PCR, the CO2, will be bad because MNO requires carbon to be reduced, while MNO2 can be reduced with CO gas. So I would say MNO2 is nearly reduced for free.
For free?
No, it's an expression to explain, because since when reducing MNO in the bottom layer, at the slag layer, since when reducing MNO, you produce CO gas. If you have no material to be reduced on the top,
Yeah, it from layer.
the CO is lost.
Here is lost. Yeah.
And so, I mean, so MnO2, if you have MnO2, it is reduced for free practically, except that you need a bit energy. You need a bit more energy, but it is not costing more carbon.
If you do not use the MnO2, we charge just the MnO.
Yeah.
It is the CO gases go outside.
It's not less gas. No. Because you see, when MnO2 plus CO gives MnO plus CO2, the number of molecules is the same. It's not less, it's not more.
If we the MnO2 plus CO reaction is then we use the used gas other reactor.
In another,
Another reactor we
you can do this.
Separate,
yes.
separate.
Separate. That's an idea. Yes.
This
Okay,
here is
okay,
MnO2.
okay. I agree.
This is the CO gas.
You can, yes,
It's just MnO.
yes. I agree. This you can do. You can separate the two steps. Yes. Yes.
It's more the competitive or about the save the energies about the have the higher efficiency.
In total, I think it will not save so much. It will not save so much because if it can be well done in one layer, in one burden, it's even better because you don't have more. If you put two reactors, you have twice losses. You see, what you save.
How about the mangan yield? Mangan reduction yield.
The mangan reduction yield here is low, but by purpose, because we want to have 30% manganese in the slag. We don't try to have high manganese yield, except if we have the poor slag process. But here we have the rich slag process. We want to have high manganese percentage in the slag. But maybe we could think about. Maybe there is a way, because the result will be anyway that you need less energy in this furnace.
Less energy.
So you can have more productivity, maybe.
I hope.
Okay, let's see how we calculate this. So here we have, you see, sorry, I go back. In 100 kilo ore, you have, sorry, this is aluminium. We have 8% SiO2. This 8% SiO2 is the sum of 3.7% Se and 4.3% oxygen. And now we say 2% of this will be reduced. This means that I on this column I calculate the kilo that I obtain, the kilo metal that I obtain, and if I reduce 2% of the silicon, of the silicium, you see, this is the kilo silicium metal. I just say it is equal to, of course, the silicium metal if I had one, in the input, which is 0 here, plus the 8%, E12, the 8%, plus this multiplied by the yield and multiplied by, you know, the mass proportion of silicium over silica. So, and this gives 0.1%, 0.1 kilo. It's actually 0.07 kilo silicon. Silicium, metal, silicon, metal. And okay, I do the same for the others. Chromium there is no, and manganese, in case of manganese, actually, you see, in case of manganese, it's a bit complex because, as I explained to you, you don't have any MnO2 left. So the manganese you recover is this you recover from MnO. So you make the calculation using only the reduction yield of MnO. So you actually ignore the initial reduction of MnO2 to MnO. But unless this, the calculation is the same. You calculate the amount of metal, which is actually 71% of the metal included. And why 71%? Here to obtain this figure, you have to test. Why? Because let's see, if I put 60%, the result I am checking immediately is the amount of manganese in the slag. And my target is to obtain 30%. And therefore, I adjust the 60 to obtain about 30%, 30.6. And but to understand it better, we have also to check the result for the slag. And before, we just see that departing with, you see, 47 kilo manganese per 100 kilo ore, we have 33 kilo metal. And in case of the iron, we have 95% iron yield in the metal, and this is the same. It is calculated the same way. And now there is something special. There is a value I will impose. This is an assumption. I want to have 7% carbon in the ferromanganese, because this is a standard. In high carbon ferromanganese, you must have about 7% carbon. So this is a yellow cell because it is imposed. And so what I do now is on the metal side, I will add this, you see, I will add all this except the carbon, and I say the sum is, I hope you understand that. I make the sum of all except of the carbon, because the carbon is not calculated. It's target, it's given. And I say the sum except the carbon must be 100 minus 7%. So the sum I have added in my addition is representing 93%. So the 100% is the sum multiplied by 100 over 93%. Agree?
Mm-hmm.
Agree?
Yes.
Agree? I give another example. I have produced a simplified example. I have produced 50 kilo manganese in my metal. I have 10 kilo Fe. And I want to have 10% carbon in my metal. How do I make the calculation? I just say that the carbon, I don't know how much kilo, but I want to have 10%. So I say these two together, 60 kilo, correspond to 100 minus 10, 90%. So the sum is 60 over 90%. This is 60 over 0.90, and this is 66.6 kilo. So what I need here is 6.
카본 빼고 그냥 다 더해주면 되는데 거기다 플러스 카본이 있으니까 플러스 카본 될 양만큼을 환산해 주다 보니까 100분율로 다시 나눠준 거죠. 그거랑 아무것도 아니라고.
Okay? Okay?
Yeah.
So in this case, but I think when we began, I had 71 here. It's more accurate, yes. And for the slag, how do we do it for the slag? For the slag, we just say that
What is it? The column UMV column.
the column. This is thermodynamic values for
Mass.
no, not for mass, for energy balance. Therefore, I don't comment it now. It is afterwards we
Okay.
will enter in this. It is, you see, these are kilowatt hours for reduction per kilo oxygen, per kilo metal, but all are kilowatt hours. And now we are only in the mass
Required
balance.
energy.
Sorry?
Required energy.
Yes. Yes. So this we see afterwards. Okay, let's see how we handle the slag. Excuse me, for the metal, you have understood how I make the sum. And having the sum, of course, it's easy to calculate the percentage. meaning that for manganese, I divide the kilo manganese through the sum multiplied by 100 to have the percentage. Understand? For iron, the same. We all divide by this by this times 100. And I check if the sum is 100%. Okay, now move to the slag. Now for SCO2, how is it calculated? Of course, SCO2, I have E12. It is the 8 kilo. Huh? Plus S. Yes. It becomes more complex because SCO2 it is not just coming from the ore, but you have some SCO2. I assume that the ash of the ore is SCO2, of the ash of the coke, excuse me. Understand? This means just nothing other than there is an external source of SCO2. And the external source of SCO2 is the ash of the coke, and the coke I'm calculating here. I'm going to explain it afterwards. Okay, but if you enter coke, you enter the ash of the coke, and the ash of coal or coke or anthracite is predominantly SCO2. So I assume it is SCO2. And you see, here I give the data 12% ash in the coke. So for SCO2, it is the sum of this, and for then we have another. You see two special cases, which are external inputs. This is for dololime. It brings MgO. There was no MgO in the coke, but I have put the cell orange, meaning that it is concerned by an external input. The external input is, you can see, is the amount of dolomite multiplied by the concentration of MgO. Okay? The same for CaO. There is no CaO. This one is 0. There is no CaO in the ore, but there is CaO coming from the dolomite as well. Okay?
어차피 이거는 계산은 위에서부터는 다 똑같은 거니까, 그지? 하나만 더 이해하면 될 것 같은데.
Okay. So two from the calculation, you calculate the upper side.
Where are you?
The MgO and CaO is
Yes.
from dolomite.
Yes, yes. It comes from this external data. And so these external data, of course, they must be added separately. It may differ from one, from manganese to ferronickel. It will be different. For another, it will be different. So you will enter this like this separately from the sheet, from the main sheet itself. Huh?
원강에 있는 양에다가 돌로마이트하고 코크를 넣어줬잖아. 거기에 들어있는 MgO나 CaO 양의 퍼센트를 더해준 거라 그냥.
그렇죠. 저것도 MN.
Okay, you may, if you want, you may do this later on. You may refine the ashes are not only SiO2. You may refine the composition of the ashes. But, the amount of slag coming from the ashes is very, very, very low. So it makes no sense to go into details.
근데 excuse me, 만약에 우리 CAO 만약에 구하잖아. 지금 수식은 보면은 임내가 CA 쪽에 복사이드 CAO 이쪽에만 돼 있잖아, 그지? 근데 만약에 CAS가 있다든지 그럼 그것도 여기 수식에 더해지든지 뭐 돼야 되는 거 아닌가? 지금 수식에 보면 하나밖에 없잖아.
예, 원강의 CA.
아니, 지금 CAO가 투입됐다고 있으니까 원강이 되는데
예.
CAS가 있을 수도 있잖아.
CAS가 있을 수
물론
있죠.
CA 메탈이 존재하는지 모르겠지만 메탈이 있다면 이 수식이 다 들어가 있어야 되는 거 아니냐 이지. 슬라브 구할 때 지금 수식이 들어가면 환경을 해놨잖아.
빠져 있네요.
그러니까 그거를 얘기를 해봐. 고기사가 딱
그것을
그거를
얘기해.
잘 보고 해. 이게 내가 나중에 전문계도 이거 안 먹으려면 어떻게 되는가 잘 생각해봐. 근데 질문 안 하고 있었던 거는 문제 생기는 거 적용하는 거 이제 그때 왜 질문 안 했어요 그래서 응? 물어봐. 그게 그렇게 돼야 되는 거 아니냐 수식이 쓰려면 무슨 말인지 이해했어?
뭐 CAO에도 뭐
다른 것도 마찬가지고
CES 같은 게 있을 경우에 이국에서는 어떻게 반영해야 되냐.
그런 것도 있어야 되는 거야. 반영이 돼 있어야 되는 거 아니야. 그래 우리가 바로 쓰지.
In the slag, you can see CAO, but it is impossible to include some CAS or other.
Yes, it is possible, but I guess what you want to say is that if we have some sulfur in the ore, we will capture sulfur by CaO. That is true?
No, I mean,
No.
I said to him when we used the Excel file, it's commonly, yeah. So we can meet many cases. So and
Yeah.
in your the equations, CaO in slag,
Yes.
and you just considered just outside CaO, yeah. But the raw material includes the CAS.
May include.
Yeah, may include the
Here,
CAS.
I have here CAS. you see.
I know. But in slag CaO, you applied just one column, yeah. Not all.
Yes,
So
you're right.
and when you make the equations, and if we input some digit figures, and then you can calculate all things. But we consider it missed the plus, and we added plus.
Yes.
It is
You're right. Yes. If you have a noticeable amount of sulfur, then you're better to add in the slag to add another column with CAS
yeah, it is one of solution, or
Yes.
you edit the
or you edit
here.
here. You
It
can
is
do
one
it.
of solution.
Yes, it's also
Yeah.
a solution.
So it is
Yes.
better. The last version you give
Yes.
to us,
Yes.
and I hope that.
You can adapt. Yes. But what is important is that you understand everything what is done here, and of course you can change, you can add something.
Yeah, that's right. But it's all members is less than you. Yeah, in our is so, and I hope that I want the common packages. At first they use it, second they study and study.
Okay.
They change it.
And then we
improve
yes.
by
Okay.
himself.
You are right.
Mm.
Yes.
변경해달라고.
Okay. Now there is one important cell, which is the cell for manganese in the slag. So the manganese in the slag is is 75%, but 75% is MnO2. Huh? So you multiply this by, you see, by the proportion, by, this is the molar mass of MnO2 and this is the molar mass of MnO. Since in the slag you don't keep MnO2 but MnO, you multiply by this and you divide by this to correct the proportion. Huh? And then you multiply by 100 less the yield. So this is just saying that the MnO in the slag, the kilo MnO in the slag, are the 75 kilo corrected by the molar mass of MnO versus MnO2, and from this corrected value you take 29%, because 71% you reduce, it goes in the metal, and 29%, 100 less 71% is going to the slag. Okay? And same for Fe, but for Fe it seems that there is 0, but actually it's not really 0. This I have to check, because normally it's not. You see, we have 95%. We should have something. We depart with the Fe2O3. Okay, this is fully disappeared, because you see, you depart with this is fully 100 minus 100 is 0, so this is disappeared, and I22 is 0. Yes, I see. This is a small mistake. It's due to the fact, because I have changed this at the same time because of the manganese. You see here, this is the mistake that there will be no Fe2O3. There will be only FeO. But to estimate it, you don't take this amount of FeO, because in the ore it is 0. You must take the same and correct it by the, like we did for manganese. You understand? We're going to correct this immediately. So instead of, you see, the FeO that you must consider is not 0, because in the ore it was 0 actually. But you must consider the Fa coming from the Fe2O3. Understand? And that's a mistake in this sheet. So here we will correct. We will put this one, and we multiply it by this over this, and now you have a factor 2 to consider. I explain. You understand? Because in the molar masses, in case of MNO, you see, in case of MNO2 and MNO, you have in both one Mn. In case of Fa2O3, you have two Fa, and in FAO you have one Fa. So here you have to correct this. You have to consider that 5 kilo Fa2O3 I explained it better. Fa2O3 is twice 56 plus 3 times 16. This is 160. This is 72. But if you have 160 kilo Fe2O3 reduced to FAO, they don't give 72. They give how much? Because here you have one Fa and here you have two. So they give 2 times. Two times 72. Okay? And therefore, I have to correct by the molar mass, but put a factor 2 here. And note. And you see, now we have something. It's very small, but it was surprising to me that we have 0. Could you take it? Could you correct it? Okay. This is okay. And then you see, here again, we make the addition. For 100 kilo ore, we obtain 46 kilo slag. And we can calculate then again the percentage of each divided MgO percentage is kilo MgO over kilo slag times 100. And in case of manganese, we calculate, of course, the percentage of MnO the same way, and in a shifted cell, because it is not to be added in a shifted cell, I calculate the percentage of Mn. You see, the percentage of Mn is the percentage of MnO times 55 over 55 plus 16. Understand? We have calculated 39% MnO. Okay? And we want to know percentage Mn, and this is 39 times, because Mn is 55, oxygen is 16, so the part of Mn in the 39% is 39 times 55 over 71. You agree? This is 71. Agree? I just explained how this is deduced from this.
MNO가 38.8% 있는데 그래서 O 띄고 MN이 30%라는 얘기야.
그대로 보면.
Okay?
오케이.
And okay, for the other elements, we don't present the percentage of the element except for manganese, because in case of manganese we have a target of 30% manganese in the slag, not 30% MNO, and therefore when we as I explained to you, when we test or when we try the reduction yield, which is giving you the target 30% manganese, you see I put 65, there we have too much. And to check this, we must have the manganese corresponding to the MNO. And so the good figure is 71%, because this gives 30% MN in the slag. And here, when we have all the percentages, we make again the check if the sum is 100, but you see we make the sum except this one, because this one is not to be added. Okay? I know there is just to be, there is a group of column that I call dust minimum. Dust minimum is the dust you will obtain even if you have no fly off, because of course in our mass balance we don't consider the fines that are flying off, that are sucked off during charging. Of course, we cannot predict that. If you have many very small fines, you will have some fly off. Normally 1% or 2% are sucked in the dedusting. This you cannot predict here, but what you can predict, if you have a lot of lead and zinc, these two for sure will not be in the metal, they will not be in the slag, they will be in the dust. And so this is calculated the same way. And if you had some lead or zinc, you would find it here. Agree? In our case, no, we have 0, of course. So, now we have, you see, we have defined the metal from 100 kilo ore, 40 kilo metal. We have defined the slag from 100 kilo ore, 46 kilo slag. What I do sometimes is a cross-checking, and you see what I have put here, but this is not necessary. It is a verification, it's a cross-checking of the amount of manganese. If my manganese balance is good, I say that the total manganese of the metal and of the slag is 40 kilo times 83% plus 45.7 kilo times 30.1, and this gives me 47.4 kilo, and this I compare with this, so it is correct. Okay. And now we go to the calculation of the carbon, because of course the customer has given the amount of coke, so we could consider, okay, the customer knows. No, it's not enough. You have to check. You have to do the full balance, and you have to determine yourself the amount of carbon. And if you find a big discrepancy with what the customer gives you, then you have to ask questions. Why and really, etc. Or is your coke composition different, etc. Now, how do we calculate the carbon? The carbon calculation is done here, and it is rather simple. You see, the key value that we calculate is the oxygen reduced. That is, we calculate from this column, which is the total oxygen. This column is the total oxygen. We calculate the oxygen reduced, that is nothing, that is just each oxygen multiplied by the reduction, yield. Meaning that you have no reduction yield, there is no oxygen removed. And so this sum is just the sum of the oxygen that is really removed by the reduction. And it is just multiplying the oxygen by the removal, by the reduction yield. You agree?
Okay, I think it will take much time.
Yeah.
I already booked a Chinese restaurant because I ordered. Yeah, because noodle. I do not ask what do you feel like, but it's my recommendation is better for you.
Okay.
So let's go outside and everyone's
Yeah.
together.